In this video, we will learn about common factors in numerator and denominator. So we have come across this when we were doing rational expressions, like how to factorize the numerator and the denominator, as well as how to cancel out the common factors if there are any common factors in the numerator as well as in the denominator. So the thing that you learn here is what is the significance of that common factor in while we are graphing a rational function. So we have adopted the convention that the numerator and denominator of a rational function have no factor in common. That is, like if we have the rational function to be s of x, where it is nothing but of the form p of x over q of x. Okay, if p and q, if they do have a common factor, then we cancel that factor, but only for those values of x for which that factor is not a zero. That means division by zero is not defined. So s is not defined at those values of x. So it means that in the graph there is a hole at those points. So for example, if we consider say s of x to be equal to x minus 3 over x square minus 3x. So this would, upon factorization, we get this to be equal to x minus 3 over x times x minus 3, right? So we see that x minus 3 and x minus 3 are common. So we can cancel that out and you are just having 1 over x. That is for x not equal to 3, correct? So that means except at those points where where the 0 is not there, that means we can cancel out those factors for which the factor is not a 0. Okay, so that means there is a, if you look at the graph, there is a that is the r of x is equal to 1 over x. So this particular graph will have a hole at 3. That is x is equal to 3. Hole at x is equal to 3. So that means that that would be the original graph of s of x. So we can check this whether whatever I said now is it true or not using the graphing calculator. If x is equal to y is equal to x minus 3, okay, divided by x square minus 3x. So at x is equal to 3, you will have a hole. So therefore r of x, s of x has the same graph as of the rational function r of x, but with the hole at x is equal to 3. So we can do an exercise problem. So I will take up exercise number 64. Okay, so find the factors that are common in numerator and the denominator. Then find the intercepts and asymptotes and sketch a graph of the rational function. You have to state the domain and the range of the function. So if I have r of x is equal to x square plus 3x minus 10 over x plus 1 times x minus 3 times x plus 5. Okay, so I will first factorize the numerator and the denominator. So I'll be getting it as x square plus 3x minus 3x plus 5x minus 10, correct? 2x. Okay, so divided by x plus 1 times x minus 3 times x plus 5. So r of x is nothing but x minus 2 times x plus 5 divided by x plus 1 times x minus 3 times x plus 5. So you have the x plus 5 to be common. So our new function is s of x is equal to x minus 2 over x plus 1 times x minus 3. So this is this would be the graph of the function, but with the whole, sorry, not w, yeah, HOLE, whole at x is equal to negative 5, with the whole at x is equal to negative 5. So the rest is like you have to find the intercepts and stuff. So that's pretty easy, that we did it in the last video, like how to find the intercepts and how to plot the points. Okay, yeah, I think you can do that, like find the intercepts, find the asymptotes and stuff, following the instructions that was given in the previous video. Okay, moving further, we will now see something about slant asymptotes. So as the name itself suggests that this is very different from vertical and horizontal. So these are called as oblique asymptotes and end behavior. Okay, so oblique asymptotes in the sense, if you have the rational function r of x to be equal to p of x over q of x, this is the rational function in which the degree of the numerator is 1 more than the degree of the denominator. That is, if the degree of the numerator is n, denominator is n, degree of the numerator will be n plus 1. Okay, so we can use the division algorithm to express the given function as r of x is equal to ax plus b plus another r of x divided by q of x, right? So where degree of r, this will be, its degree will be less than degree of r of x is strictly less than degree of q of x, correct? Sorry, this is degree of q of x. Okay, and a is not equal to 0. So this means that as x will tend to plus or minus infinity, so if this term will be tending to plus or minus infinity, and what happens to r of x and q of x? R of x divided by q of x will tend to 0. So for large values of the absolute value of x, then the graph y is equal to r of x will approach the graph of the line, will approach, sorry, yeah, so yeah, I was right, approach, okay, approach the graph of the line, y is equal to ax plus b. So then we say that this particular line is nothing but the slant asymptote or oblique asymptote. Okay, so to see an example here, so I take the same example as that of the one that is given in the book. R of x is equal to x square minus 4x minus 5 divided by x minus 3. Okay, so in this case, what are the factors of the numerator and the denominator? So you can write the numerator as x plus 1 times x minus 5 divided by x minus 3. So what is the x-intercept? X-intercept is the zeros of the numerator, correct? So x-intercepts are -1 and +5, correct? So after solving, x plus 1 is equal to 0, we get x is equal to -1 to be 1, 0, and x minus 5 is equal to 0 implies x is equal to 5 is 1, another 0, correct? So that those are the these are the x-intercepts. So now coming to the y-intercepts, substitute x is equal to 0 in each of the factor. So you will get to be negative 5 over negative 3. So that would be 5 by 3. So this is the y-intercept. Okay. So then the vertical asymptote, we have found out how to find out vertical asymptote. The zeros of the denominator. So zeros of the denominator is nothing but positive 3. So this is the vertical asymptote. And okay, and the horizontal asymptote is nothing but because the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. Okay, there is no horizontal asymptote. So next, let us see what is our slant asymptote or oblique asymptote. Since the degree of the numerator is 1 more than the degree of the denominator, right? So that is, degree of the denominator is 1 and degree of the numerator is 2. So we can write the function like by dividing, do the long division. So that would be x square minus 4x minus 5. So if you divide that by x minus 3, so what are you going to get? X minus 1, correct? So x square minus 3x divided by, so this would be negative x, negative 5, and this would give us x plus 3, and the remainder is 8. So using the division algorithm, if you have to write r of x, that would be x minus 1. Okay, x minus 1, that is the quotient, minus 8 divided by remainder divided by what is the divisor, that is x minus 3. Okay, you can write like this using the division algorithm, right? So seeing this, we said that this particular term here, it is of the form y is equal to ax plus b, where a is 1 and it is not equal to 0, right? So a is 1 and b is negative 1. So in this case, this would be the slant asymptote. Okay, so the slant asymptote, SA, as I abbreviate it, this is my abbreviation, or the oblique asymptote is nothing but y is equal to, the line y is equal to x minus 1. Okay, so if you graph it, like use the values, additional values, and the method that we learned in the previous video, and graph it and check, you can see that if you plot the graph, your x minus 1 would be slant, and you can see that it is approaching both the graphs. Okay, I will just plot the graph to show you. Yeah, so what we were given, y is equal to x square minus 4x minus 5, correct, divided, sorry, okay, divided by x minus 3. So the graph looks like this, and our x minus 1 will look like, if I need a pen, okay, x minus 1 will look like a line that passes through 1, and you can see it is closely approaching the graph here as well as here, correct? So that means that that is an asymptote. So it is as the x value increases, it is approaching to some value of the graph, and as x value is decreasing, if you go downwards, the line is approaching the graph, like it is not equal to the graph, but it is approaching the graph, it is going closer and closer. So that is the that is nothing but the nature, or that is how your asymptotes look like, the lines, the vertical as well as the horizontal or the slant asymptotes look like. Okay, so with this we will also think of the end behavior of the graphs. I think you have learnt about the end behavior in some sections before. I do not exactly remember which are the sections, so you can go through them and just apply it to the rational functions. Like, how does your end behavior, how does the rational function behave at the endpoints? Like, okay, so you just have to graph the function and check how does it behave at the endpoints. Okay, so this will complete the section 3.6. I have to assign you quiz questions. So quiz 3.6.4. okay, so this is nothing but problem number, okay, problem number 70 in the book. Okay, and that is like you have to find the slant asymptote 70 and 72. Okay, and to find out the common factors in the numerator and the denominator and write how your graph looks like, you can do problem number 66. Okay, oh, I messed this up, I'm sorry. 70 and 76. Okay, and 66. Okay, so you can write this in ascending order, like 66, 70 and 76. So that is your quiz 3.6.4. so the next videos will be on section 4.1. That is you will learn about exponential functions. So you know how exponential graphs look like for small change in input values, the output value will be increasing to a greater extent. Okay, so then we say that there is an exponential raise. You might have heard that when firms or marketing people or some people, they discuss about their performances and things like that. If you see during a short period of time or for a short change of input value, if you see a very high raise of the output value, that would be nothing but an exponential growth. So we will see about functions of such type and learn more. Okay, thank you for listening and see you soon with section 4.1. Thank you.